Software architecture is about identifying the trade-offs that are relevant for your particular context. Only these trade-offs are rarely discussed. So today, this is what we'll talk about. We'll react to an article that describes 10 trade-offs every system design engineer must master. And when we say system design engineer, to me, it's basically the same as software architecture, but we'll talk more later. Welcome back to Think Design Work Smart. I'm Alex Bolboaca and I'm coming at you from the Mozaic Works studios. And today I'd like to discuss trade-offs. And we'll talk about trade-offs with this article published on July 21st, 2025. 10 trade-offs every system design engineer must master. Created by Rocky Bhatia. I hope I'm pronouncing the name correctly. And he also has some nice diagrams, but you can see the link in the description if you want to read this article by yourself. I'm just gonna go briefly through some of these. If you want to learn more, there are a lot more details that you need to take into account. And this is just looking at the surface, looking at common trade-offs, but in reality, when you think about things in your specific context, it gets a lot more complicated than that. But at least it's a good conversation about trade-offs, what trade-offs are, and why, which trade-offs we need to take into account. Now, before we move on, let's clarify what trade-offs are in the context of architecture. Basically, you always, when you make a decision related to software architecture, you always have good things and you have downsides. You have advantages and disadvantages. You can think of them like this. And usually you can look at 2 or 3 different options and come up with advantages and disadvantages for each of those. And that's what we mean by trade-off. When you choose a solution over another solution, you're making a trade-off. You're trading, for example, performance for security. This is a very common trade-off. How do you get more security? Well, you need to add more checks, more cryptography, more digital signatures, more certificate management, more password, more different algorithms, and so on. All of those take some extra processing time, which means you're trading performance for security. You're getting higher security, lower performance. Depending on your system, this trade-off can be acceptable. For example, if you have only a few requests, then it doesn't matter. Or it can be very painful because it might happen that in order to process those increased security checks and do the algorithms and so on, you might need to pay for extra infrastructure. And if you have a lot of requests, that might cost you a lot more. So that's the thing with software architecture. You can always find with this analysis alternative solutions that initially sound better, but then when you start to go into details, you realize that there's another trade-off involved. So one rule of thumb, there's never a decision without trade-offs in software architecture. If you haven't found a trade-off, it just means that you haven't found it. It's not that your decision is perfect. You haven't found the trade-off yet. And you might eventually find it when it will hit you. It's better to know about it beforehand. Now let's talk about some of these. And once again, I'm inviting you to read this article. It's good, and to go into more details on the topics that interest you. First of all, vertical versus horizontal scaling. When systems grow, they need to handle more users, data, or traffic, but how you scale makes all the difference. Vertical scaling, scaling up, means you're basically getting better servers. So if you're using cloud, you're switching from a lower instance to a higher instance, more memory, more storage, whatever you need, more CPU. Or you can do horizontal scaling, which is scaling out. So you add more servers. Now, vertical scaling, simple to implement, just upgrade the box, has physical limits. There's only so much you can add. It's a single point of failure, still one machine. Horizontal scaling, it's highly scalable, keeps adding servers, fault tolerant. If one node fails, the others run. But it needs more effort, because whenever you do this, you need load balancing, right? You need to add a load balancer that will distribute the requests between the different servers. And then in order to do that, you need stateless services. And you might need to do sharding. Sharding means splitting the database into smaller pieces, and then the routing of the load balancer uses specific algorithm. So let's say you have customers, you can have A to C on one server, D to F on the second server. I'm simplifying. Generally speaking, you'll take statistics and split them into relatively equal shards. And the load balancer would look at the customer name and redirect you to the right server. And that could be sharding. Or they could have the same database, which means there has to be some kind of synchronization there. And if you do that, then the load balancing is based on the load on each server, but you're paying with the synchronization part, which can also be faulty. So if the network goes down, you could have additional issues. Real world insight, scaling up is like upgrading a delivery truck. Scaling out is like adding more trucks and managing a fleet. Yeah. Pro tip, use vertical scaling for simplicity and prototyping. Use horizontal scaling when you are thinking production grade, distributed, and future proof. Right. Second one, very interesting. SQL versus NoSQL, more than just a schema choice. Yeah. Actually, SQL versus NoSQL is rather schema versus schemaless. Do you want to have your schema in your code, or do you have to have your schema in your database management system? That's the choice. SQL and NoSQL solve different problem. The right choice can make or break your system at scale. And they also introduce new SQL. So SQL data structure is structured data with a predefined schema. NoSQL, flexible and dynamic schemas. You can handle structured, semi-structured, and non-structured data. I kind of like this about NoSQL. So if you have a bunch of CSV files of different types of files that you want to load into a database and then search based on various criteria, that's a good way. New SQL requires a predefined schema, but is more flexible than traditional SQL. If you talk scalability, SQL can scale vertically, but is difficult to scale horizontally. NoSQL can handle vertical and horizontal. ACID compliant. SQL is ACID compliant. This is basically that it ensures a transactional behavior, to simplify. It's more complicated as usual, but we'll simplify for the goal of this video. NoSQL typically has no ACID compliance. NewSQL has ACID compliance. What about consistency? Well, of course, we have high consistency in SQL databases. We have eventual consistency in NoSQL databases, and we have strong consistency for NewSQL. What is the query language? SQL or database base languages for NoSQL. MongoDB query language, Cassandra query language. They each have their own query language, which tends to be based on something like JSON or roughly that type of syntax. You can have complex queries in SQL and NewSQL, but not in NoSQL. They are limited. So the design trade-off is that SQL gives you trust and structure, NoSQL gives you speed and scale. Which one do you choose is based on the data patterns that you see. Access patterns, how frequent are the reads, heavy writes, the consistency needs, can the data go stale, query complexity, do we have joins, do we need them? Pro tip in interviews, say I'll start with SQL for transactional integrity, but if we hit scale or need flexible document storage, we can evolve parts to NoSQL, especially for logs or if you like data. Well, that's a good general approach, but I would also consider the patterns. So depending on the patterns, and I can give you a few examples. For an e-health product that I worked on, we had to implement a service that would search for drugs in a drug database. We were licensing that drug database, buying a license for it, and we got updates. And it contained basically all the drugs available in each country in EU and under which brand names and chemical composition and so on. And what we needed was to search the database through a service based on drug name, generic drug name, brand name, the various dosages and so on. There's a lot of stuff there. And so in that case, it was basically a read type of service. The database came in, I believe, CSV files. So in that case, MongoDB was pretty useful because MongoDB had issues back then. I'm not sure now, but it had issues with writes. We didn't care about writes. We were basically getting a new version of the database, importing it into MongoDB, and then the service would retrieve the data read-only. We never wrote the data from our code, we only imported the data. So that's one situation where MongoDB was very good because it simplified the import a lot. Since we didn't have a schema, it was much easier to do that than if we had a schema. We had to do less work, and it still worked pretty well and also fast and so on. So there are situations where the choice can be relatively obvious, but there are some where it's not as easy. Sync versus async processing. Imagine you walk into a coffee shop, place your order, and wait at the counter until it's ready. That's synchronous processing. Now imagine you place your order, receive a token, you see chat or work, and your coffee arrives when it's ready. That's async processing. Or like in Starbucks, was the Starbucks model. You go there, you pay, and then you wait at the end of the line for... That's a queue-based process. So when to use sync, you need immediate user feedback. The operation is quick and deterministic. Failure needs to be known immediately. When to use async, tasks take longer. You want to decouple services. You need to absorb spikes in traffic via queue. Real-world implications, async is harder to debug. You have logs, retries, dead letter queues, but more resilient. Failures don't block the whole flow. Pro tip, in interviews, don't just say make it async, say we can process the request synchronously for the user-facing part and in queue secondary tasks for async processing. This improves responsiveness while maintaining reliability. Well, interesting. I would say, yeah, I have a bunch more thoughts here, but I won't go into all the details because it will take quite a long time. But you can see the way I'm thinking if you watch the choreography versus orchestration video. Batch versus stream processing. How fast does your data need to be processed? To caching strategy, yeah, so batch versus stream, that's only one. The question determines whether you go batch or stream. So stream processing requires, is basically real-time processing, but the problem is you need to ensure real-time speed for processing. It's best for things where you really need a real-time ticker, like stock exchange or weather or news. Those are things where you might need stream processing. For batch processing, if you have a report but that you need to build, but it can wait 4 hours, no, it's okay. You can do batch. Read-through versus write-through caching. Two caching strategies, same goal, faster reads, different philosophies. So read-through, if data is present in cache, read from cache. If data not present in cache, read from DB. Return data to application. Write-through, application writes data to cache. Cache writes data to database immediately. So read through caching, the application queries the cache first. If there's a cache miss, the application fetches from database. It's simple and reactive, only fetch what's needed, works well for read-heavy systems, but cache might be stale unless eviction policies are well tuned, which is one of the biggest problems with caching. Use case, product detail pages, user profiles, dashboards. Think of it like don't preload, just fetch and save what I asked for. Write-through caching, every write operation updates both the database and the cache. Cache is always in sync with DB, but it adds write latency, and if the cache layer fails, writes may fail too. Ideal for read freshness critical systems like real-time pricing, stock levels. Use case, e-commerce inventory, price updates, real-time financial data. Think of it like if it changes, update everyone at once. And let's take another one, REST versus GraphQL. The API interface were both powerful modern apps, but they solve very different problems. REST works with multiple fixed endpoints. Data is served in predefined shapes, mature, well supported, easy to cache. Yeah, particularly if you use idempotency correctly for REST, which, let me tell you, it's rarely the case based on what I've seen in the wild. Use case, CRUD apps, admin panels, traditional backends. You get what the server decides, simple and structured. GraphQL, single endpoint where clients query exactly what they need, reduces overfetching. It's ideal for complex UIs and mobile apps, but requires schema management, query complexity control, and validation layers. Use case dynamic UIs, mobile first apps, microservices, gateways. You ask for exactly what you want, powerful, but it needs guardrails. To me, the difference between REST and GraphQL is mostly in the querying. REST is really good for if you are doing it correctly and actually splitting your resources and thinking of resources as the engine of your application, then it really pays off. But REST has one fundamental issue, and that is queries. Queries are not really captured in REST. So the way you do queries is by implementing various parameters or endpoints, and this is the problem that GraphQL solves nicely. But GraphQL can lead to a coupling between the interface and the database, which you want to avoid. So GraphQL is perfectly fine if you define your schema separately from your database. You need to define the schema of your resources available through the API, and that is separate from the schema of your database. Otherwise, every time you need to modify the database, you need to modify the callers to the service, which is really bad. Really bad. It's hidden coupling. It's one of the worst types of hidden coupling. So this is another trade-off. All right. I think that's it for now. If you want me to keep going with this or discuss more trade-offs, let me know in the comments. I love comments. And if you have any curiosities about software architecture, about cybersecurity, about AI, this will be the main topics for this year. Probably spiced with some other things, because I expect other things to happen as well. Anyway, let us know in the comments and let's have a conversation about all that. Thank you kindly for the view, and until next time, remember to think, design, and work smart. See you next Saturday.